Okay, this is the last hour of Physics 1B for September 8th. We just talked about a barometer. I was saying during the break that there are other methods to measure pressure that we're not going to talk about immediately, but you can look them up yourselves. The manometer is something else discussed in your book, and that's what this problem is about. But it really only concerns the way in which these fluids are going to balance against each other, so it's not super important that we know what a manometer is in order to do this. We just need to understand what's happening in this blurry picture here. So it says a manometer tube is, I don't actually know how to pronounce this. Is it manometer? It's probably manometer. I don't know. It's partially filled with water. Oil, which does not mix with water, is poured into the left arm of the tube until the oil-water interface is at the midpoint of the tube. So in our tube, what we have is we have some water over here. We have some oil over here, right? And there's a place in the middle where they come in contact with each other but do not mix. So the water stays on the left, the oil stays on the right, and we've poured just enough on both sides so that the point where they mix is right here, right in the middle, or point where they meet. Okay, so it says both arms of the tube are open to air. Find a relationship between the heights of the oil and the height of water. That's what we want to do. What's the relationship between the height of the oil relative to the bottom and the height of the water over here? Do you all want me to draw another version of this picture so it's not so blurry? I don't know that it matters, but I will. Donald says, I wonder what the maximum pressure could be. Like, just what is the maximum allowed possible pressure? That's what you're asking, Donald? It's a really good question. Now, if it's a pressure that we measure via something like this, then the limit on how high it could measure would be limited by how tall the tube is, basically, right? So if our tube was a meter tall, then the highest pressure that it could measure would be 1,000 millimeters of mercury, which would be approximately like 1.3 atmospheres, right? That's if this thing was 1 meter tall. If we make the tube 2 meters tall, it can now measure up to 2 meters of mercury or 2,000 millimeters of mercury, which would be about 2.3 atmospheres, or maybe like 2.2 atmospheres or something like that. Yeah. It's completely dependent on how tall you make that tube, Donald. Otherwise, if you don't make it tall enough, then well, it's not gonna be able to. There's gonna be a limit to what it can measure. All right, coming back to this problem right here. So basically, what we have is there any way I can draw this without it being like super nasty? I don't think so. Not with one of these things. I guess I can make the line straight, but we'll just try. So we've got a U-tube. Tube right here. And in our tube, we have two different fluids. On the right-hand side, we have oil, which we'll make yellow. And our oil comes up to a certain height up here. That's the top surface of the oil. And on the left-hand side, we have liquid water. And our goal here is to say, how is the height of the water related to the height of the oil? You know, as bad as my picture looks, it is still much more pleasing to my eyes, at least, than looking at this blurry nonsense that happens whenever this book gets converted into a PDF. So, we want a relationship between the height of the water and the height of the oil, and the one thing I also hate about the textbook is that these pictures, they tell you too much information. They tell you way more information that they're going to tell you in, I think it's blocked off. Here, we'll just block it off like, kind of like that. It doesn't help. It's a good place. I can put it here. There we go. We're going to put the problem down there because I hate how much they show as information in those problems. On your homework problem, this is what it's going to look like, right? You have a homework problem that's like this. You have a lab and a problem that's like this. This is all you're given, okay? So what do we know that's going on here? So because there's a column of water and because there's a column of oil and they have a certain height, we know that these columns exert pressure, right? And we also know that if it's open to air, that's what it says in the problem, right? It says, where does it say it? Both of the arms of the tube are open to the air. You need to get used to understanding specifically what this is telling you. When they say open to the air, up here and right here, that means that the pressure that's acting down on the top on both sides is just atmospheric pressure. Stop it. Stop doing it to shape. We know that the pressure on the top is basically just air pressure. So there's one atmosphere of pressure that's acting down on the top on both of these sides. In addition to that pressure, when you have a height, let's say of water, because we've talked about this a lot, there's going to be more pressure down here at the bottom. Would everyone agree? There's more pressure down here at the bottom. Because you have the pressure at the top plus a height of water, and we know there's this connection that the pressure at the bottom has to be equal to the pressure at the top plus the density of the fluid times G times H. We just used it in the last problem. Or in discussing how the mercury barometer works. So we know that the pressure down here is more. Now, if they're balanced out, meaning that the oil's not pushing the water to the left, the water's not it's at equilibrium, right? Then it has to be the case that the pressure is the same for both of these. After all, if the pressure of the oil was greater than the pressure of the water, it would push the water back to the left. If the pressure of the water was greater than the pressure of the oil, the pressure from the water would push the oil back to the right. Does that make sense? If the pressures were not the same, then it would kind of have to move until they made an equilibrium, until an equilibrium was found, basically. And so here we are at equilibrium, and the pressure at both interfaces here has to be exactly the same, and that's the key to these type of problems. If the pressure is the same for both of them, right, then we can say, for each one of them, that pressure should be equal to P naught, so let's say for the water, for example. For the water, the pressure should be equal to P naught plus rho water times gravity times the height. And then for the oil, it should be the case that P is equal to P naught plus density of the oil. And I realize here, this should be height of water. My bad, they're different, right? Height of water. Rho oil, G times H oil. And then we can make these equal to each other. So we can just say, okay, well, this is equal to this, because the pressure at the interface has to be the same. The interface is this point right here. We're calling that the interface. Right, so they're equal to each other. So the pressure of the atmosphere cancels out. And a G will cancel out, but we'll do one more step first. So we get density oil, G, height oil, equals density water, G, H, water. Gravity cancels out from both of these. And we get that. Our goal was to find a relationship between the oil and the water. So let's do height of oil divided by the height of water should be equal to, so I divide the water to the left-hand side, that means I need to divide the oil over here. On the right-hand side, then we'll have density of water divided by density of oil. This feels wrong to me. It feels like they should be a direct relationship, but let's think about it for a second. I mean, it looks right. It looks like the math. Did the math make sense to everybody? Let's pick some numbers and see if it makes sense. So we know what density of water is. The density of water is 1,000. Oil is usually less dense than water, I think, right? Because you can float oil on top of water, right? You can pour water into a glass and you can pour oil right on top of it, I think. Is that right, or is it the other way around? I don't really remember. Density of oil. Let's do, like, I don't know, vegetable oil. So there's a wide range of densities. So let's say that we choose something in the middle, and we choose 1.2 kilogram. So let's say we choose density oil to be 1200 kg per meter cubed. It looks like oil can range from 0.9 to like 1.4. So we're just choosing something kind of in the middle, right? Okay, and let's pick some numbers too. Let's say the height of the water is equal to, I don't know, let's say half a meter. It's a big number, but it doesn't really matter. We just want to see what we get for an answer. Let's calculate what the height of the oil would be then. According to our equation, the height of the oil would be equal to density of water over density of oil. So that's 1,000 over 1,200 multiplied by 0.5 meters. And we get that the height of the oil, in this case, would be less than the height of water. And we get, I should have chosen 0.6, 0.5 divided by, or times 1 divided by 1.2. So slightly less, you get 0.42. So does this make sense? Yeah, I think it makes sense, because if the oil is less dense than water, if the oil is more dense than water, then the height of oil you need should be less than the height of water you need, right? Right? Yeah, it makes sense. If the oil was less dense than water, then the oil column would be shorter. No. What's happening in the problem, in the picture, just to be clear here, in the picture, it's more something like this. In the picture, what's happening is the density of the oil is less than the density of water. Would you all agree? In the picture? Right here? It looks like H oil is higher. So if you replace this with a smaller number to make it make more sense, we put 900 for the density of oil, right? So I've changed this number in both cases. Then the height of the oil will go higher, right? Because you'll need more oil. So if we choose that, then we do 100, or basically just 10 over 9. 10 divided 9 times 0.5. And then you would need a higher density of, or a higher height of oil. Okay. So just plugging in different numbers to see what we get, to make sure it makes some kind of sense. And it looks like you went and looked it up and you agree that it's the right equation. So that's our equation. You're going to see this show up on your homework, like I say. So hopefully it will not come as too much of a shock to you at that time. Anyone have any questions? Alrighty. This will probably be the last thing we have time for. I don't know. Maybe we'll be able to start talking a little bit about some other stuff. But so there's a couple problems on your homework that you're going to see that your textbook just straight up doesn't even talk about. I don't know how they get away with doing this with textbooks. I really don't. But that's just how it's always been, that in a physics textbook, it's very common that your homework problems will introduce you to new ideas that you haven't been exposed to, and you have to just kind of do your best to try to learn from them. So what I did was I found another textbook that covers this topic, so that it won't be so foreign to you when you see it on your homework. You know what I mean? My goal is always to make sure that when you go home, you have at least enough, you're armed with enough to be able to at least start your homework, okay? So what we're going to be doing on this problem is looking at the force on a dam, okay? So here's our dam. You can see that it's drawn three-dimensionally here. You can see that the dam is kind of curved so that there's more material holding back the water at the bottom. On the left-hand side, it's a dam. So what does a dam do? Well, you dam up a river in order to create like a reservoir, so you can, use the water to flow over a turbine and create electricity for you. Hydroelectric dam, right? Or you dam up a river to use as a water source. There's probably other reasons why people use dams. I'm definitely not an expert in this at all. But the idea is that there's water over here, and it's being held back by the dam. I guess another reason that you create a dam is just to create a fresh body water like a lake. They did that a lot in the state that I'm from. My state, Oklahoma, has, I think, only one truly natural, like, large lake. So they created a bunch of lakes by damming up rivers and, creating a lake because they've dammed the river up. And then they just release water when they need to control the level of the lake. Okay. So anyway, water being held back by a dam, right? And it says the water is filled to a height h behind the dam of width w. So w is the width from left to right of the dam. So we do assume that there's like an enclosure of water right here. We wanted to determine the resultant force exerted by the water on the dam. So we want to find the force of this water acting on the dam. Before I start talking again, does the setup or does the picture make sense, and does what we're trying to solve for make sense? We want to find the total force on the dam. The dam being the gray thing in this picture right here. Does at least what we're trying to do make some kind of sense to you, even if you don't know how to do it? Okay. So again, I'm going to draw my own picture. We'll come back and we'll refer to their picture in a second as well. But first of all, I'm just going to draw my own picture. So we've got the dam. Oops. And so here's our straight line for the dam. The dam is shaped kind of, it almost looks like it's shaped like a parabola or something, doesn't it? Maybe it is. Maybe that's what they do. Maybe they shape these like parabolas. I guess we'll know more after we do this problem. So there's our dam, and it's three-dimensional, so we got to give it some three-dimensional nature here. And it's holding back a bunch of water. Oops. There we go. It's holding back a bunch of water, and here's our water over here. Let's say the water comes up to this level. All right, so it's holding back all this water back here. And the total height of the water that we have is h from top to bottom. Just down to here. And then we also have a width w. So there's my picture. Over here we have water. Over here we have dam. And our goal is to determine the resultant force exerted by the water on the dam. Now let's set up why this is a difficult problem first. So the first thing to say is we're trying to find force on the dam, right? Force on dam. And really, the only equation that we know about force related to liquids is, what is that equation that we know about how force is related to liquids? What have we learned about this in this particular class in the last week and a half or whatever? Pressure is equal to force divided by area. That is exactly right. That's the only equation we have. So pressure is equal to force divided by area, which if we rearrange it, says that force is equal to pressure multiplied by area. Well, that's easy. We just need to figure out what the pressure of the water is, right? And then multiply by the area of the dam. Well, the area of the dam, that's easy, right? What's the area going to be? What's the area of the dam? It would be the area of this face of the dam here, right? So W times H, right? W times the height, H. That would be the total area of the dam. Okay. What's the pressure of the water then? What's the pressure of the water? What do we use for the pressure of the water? By the way, all the ice melted in this. I don't know if you all care. And I'm almost certain you can't even see, because I marked, I should have used like a rubber band, but I couldn't find one. Point is, I did this demo. This thing is covered in Uh, can you see the mark on the glass in the picture? I doubt it. I really doubt you can see it or not. But there is, I put a little marking there, and it did, once all the water melted, it's still at the same level, basically, right? Okay, so Astro Lover says P naught plus rho GH. That's definitely going to tell us the pressure, and that indicates something that is hard about this problem. The pressure of the water is not a constant, right? The pressure of the water is not constant. We know that the pressure is going to get higher and higher and higher as you go deeper and deeper into the water, right? Does that maybe tell you why it is that you might design the dam such that you have this more fortification, more material down here at the bottom than you do at the top? The pressure at the top is very small, but the pressure at the bottom is really big, right? So you need to have more material down here to deal with the fact that the water pressure and the pressure acting on that portion of the dam is going to be a little bit higher. In fact, we can exactly calculate how much higher the pressure is down here than it is up here, because we have the equation that you just wrote. Pressure is equal to pressure at the top plus rho GH. Okay. Pressure is not constant, which means that this equation is not exactly going to work for us. This equation right here is going to have to be modified. And the way that we're going to do this, and this is going to be something you're going to see happen consistently. If you've taken Physics 1C, you've probably seen a lot of problems like what we're about to do, and perhaps in 1D as well, although I don't know. What we're going to do is we're going to say, I don't know what the force is on the whole dam immediately, but I can tell you that I know what the pressure at every point on this thing is. I know what the pressure at every single point on this thing is. It's given by that equation. So what if I figured out the force on like a piece of the dam, like let's say this red strip right here? What if we found a force just on that one piece and then use some type of mathematical technique to sum up the forces on the entire dam? That's our strategy. Our strategy is going to be, say, I find the force acting on a small piece of the dam, and then I sum up all the forces acting on the dam. That's what we're going to do. All right? So our strategy is going to be find the force. We're going to call this force, just to introduce you to it before I do it, dF acting on a small section. We're going to call the section dA of the dam. And then we're going to add up all the dFs. So what we're going to do is we're going to say, we take our object, right? We're going to cut out from our object a sliver. How much of a sliver? A really, really, really tiny sliver, okay? And we're going to say that sliver has an area that we're going to call dA. That's going to be the area of this piece right here that we cut out. And we're going to say it's subjected to a force that we're going to call dF. Why do we use dA and dF? Well, maybe you already know, but this is going to involve calculus. And when we talk about tiny little cuts of an object, we call them a dA, which is like a differential A, or the way I think about it is it's like a little tiny piece dA. That's all it is. It's a tiny piece that has a size dA. You know, like in math, like sometimes you might see this type of thing that you write down x plus dx. When you write x plus dx, you're talking about some distance x, right? And then you're adding onto it some distance dx. And that's just a little tiny addition, right? X plus dx, or x minus dx, you might see this kind of things. So dA is a tiny piece of area, where area is normally just width times height, right? So the water at this location, at this level, has some pressure P, right? We know the water at this level, the water has a pressure P that's equal to this. where h is the distance measured from the top. So we have this height h from the top right here to here. That actually looks worse. Let's write it on the dam. We'll put it right here. If I know the height h down to this point, and that means that I know the pressure, then I can calculate the force dF acting on this strip dA by saying that the force, we're just going to look at this equation, right? Look at that equation. And we're just going to put on the left-hand side, dF. We're going to write the pressure is just going to stay P, and then we're going to change the area to dA. Have I changed the equation in any way? No, not really. I've just changed it from being force equals pressure times area to small amount of force is equal to pressure times small amount of area. That's all we've done. That's all we've done. Does this make sense, what we've done so far? Does anyone have any questions? Yeah, no DP, why not? Well, the reason why is because all along this particular strip, dA, the pressure is constant, right? Even though the pressure changes with height, all along that strip, because I made a like a lateral or horizontal strip, the pressure is constant along the strip. Does that make sense, Troy? The pressure is the same all along the strip. Now, had I chosen a strip like this, that wouldn't have worked, right? Because now the pressure would change from point to point on the strip. But because we intentionally chose a strip that went left and right, I know the pressure is constant there. Same depth, yeah. Okay. So now we need to do a little more work here. We need to set up a coordinate system because we're not really going to be able to solve the rest of this problem without one. You can see on the picture they've already done it here. So this is going to be the positive x direction, which I don't think we're going to need. And this is going to be the positive y direction pointing up like this. Now the reason for this is because then we can define, if the height from the top to the bottom is h, I can define the height from that point to the bottom to be y. And that way I can measure y in the positive direction. In addition, what we can do, and this is much better seen on their picture over here, we can define the thickness, right? The thickness at any point along here we can call dy. And I don't know if I can really draw that on here, but the thickness from here to there is dy. That's the thickness of our thing. Now this is where I've drawn our picture here, and you can see it's now become exactly what the picture on the left is, but I just wanted to show the steps as to where we got to where we are. Now, the process by which you solve problems like this, where you have to like break things up into individual parts, is you now need to turn everything into variables that make sense. So I usually start off with dA. What is dA? dA is the area of the strip that we cut out, right? So what is area, not R? What is it equal to in terms of the variables that are given on this picture right here? So look at the picture right here. I'll get rid of this shit, of the stuff that I drew on here. Sorry. What is dA in terms of the variables given right here on the picture? We're rapidly running out of time. We have 6 more minutes. We can do this. What is dA equal to in terms of the variables in the picture? It's going to be the area of the strip. dy times w. That's exactly right, Donald, because area is just width times height. The width is w in this direction. That's w. And then height is dy. So you get dy times w exactly. So we're going to write it as w times dy. What else do we have? Well, we have the pressure. The pressure is defined like this. Ooh, I got to go down a little bit because you can't see what I just wrote. So what is the pressure? Well, the pressure is P naught plus rho GH. Let's write that over here. Pressure is P naught plus rho G. Now, what's H equal to? Well, H is little h right here, is the height, but we know that it's related to big H and Y. And I would say little h is equal to capital H minus Y. And I'll write that up here. Can you see that? H plus Y is equal to big H. solve for little h, you get h minus y, right? Okay. So we got that. We got that. We're actually almost done. We will solve this problem very quickly here. So before I make the next step, does anyone have any questions? Any questions? What we did, does that make sense after I put everything together? I replaced the p with p. I replaced dA with dA. And that's all that I've done. So the next step, anyone know what the next step is? Anyone take a guess? How do I now, our strategy, remember, was to find the force dF acting on a small section dA of dam. We've done that, right? We got everything in terms of one variable, y, and a bunch of constants. We've done that. And then it says to add up all the dFs, and that's right, Astrolover. The way you actually add everything up is you use an integral. Because as you know from studying integrals, integrals are kind of a limit of a Riemann sum, and so it's a way of summing up a bunch of things. An integral is basically just a sum if you think about it. Left-hand side is just going to become f. We're going to integrate from, we're kind of running out of time here, so I'm going to jump through the end of this. We're going to integrate from y equals 2, our variable's y, right? We're going to be integrating from y equals 0 up to capital H, because that's after all the values that y can take on. Down at the bottom, y would be 0. And up at the top, y would be h. Remember, there's a bunch of strips that we can cut out here. So the right-hand side of our equation is going to be this integral right here. It's all integrated with respect to dy, right? So the first part of the integral is going to be p naught. What do I get when I integrate this times dy? What happens when you integrate? This is basically it. There's two different integrals. There's this one, p naught w dy, right? That's the first term. What do you get when you do this integral? P naught wy, exactly. You just get a y, right? Because this is like integrating a constant. Okay, might not look like a constant, I know, but from 0 to h plus rho g h w dy. We're also going to get a rho g h. There's a w that's on every term, and if we integrate that, if we integrate this one with respect to y, again, capital H is a constant. It's the total height, and we just put another y on here. We're going to do that from 0 to h. Plus the last term, which has a negative sign in front of it. So there's a negative sign here. So we'll have minus. The last term is rho g y w, and there's a negative sign, but now there's a y dy. So when you integrate that, you're going to get y squared over 2, right? Or 1/2 y squared from the power rule. So we're going to have negative rho g w y squared divided by 2. Also from 0 to h. Does that all look right to everyone? I'll scroll down because I got blocked off a little bit. Can everyone follow what we just did? First term is a constant, so you just put a y. Second term, rho g h, that's a constant, so we just add a y. Every term has a w in it. Final term is rho g, there's a negative sign, and it's y dy, so integral of y dy is y squared over 2. Okay, this is the end. We're out of time, so. Where's the 0.5 coming from? Integral y dy is equal to y squared over 2. Yeah, Troy, that's what it is. Okay, so let's solve this out. So what do we have? Well, obviously every term has a W in it, so I guess we could factor that out. First one's going to be P naught times H. The second one's going to be rho G. We're plugging in H here. It looks like H squared times W, or rho G H squared, yeah. Because you plug in H for Y and you get H times H. And the final one is going to be minus rho G. Now we plug in H squared over 2. So our final answer is F is equal to P naught times H times W. And then these two terms, they subtract away, so you're going to get plus rho G H squared. There's also a W in this one divided by 2. So that's the force. And if we look back at the problem, it only wants us to determine the resultant force exerted by the water on the dam. So I realize now that actually this is the force of the air, right? So the force of the water, this is the total force. The force of just the water is the second term. I forgot that part. Rho G H squared W divided by 2. And that's the answer. Because the first term is the force of the water. This piece right here is the force of the air. And we only wanted to find the force of the water. So that's the answer. I know that problem's kind of complicated, and I probably went through it a little too quickly, even though we spent almost 20 minutes on it. It's still quite complicated what we're doing here. So if you need to review it by watching the video, might be a good idea. Definitely going to see problems like this on your homework, so I wanted to show it to you in advance. I believe I've covered all the topics that show up on the homework that's due Monday at this point, so you should be able to solve it with no problem. I think we've covered everything in a high enough detail that it shouldn't be too challenging for you. I mean, it will be challenging. It wouldn't be a good homework assignment if it wasn't even like a little bit challenging, so it needs to be a little challenging. Yeah, so I think I've covered all the material. So I'll stick around and answer some questions. I can't stick around too long. I have a class in like 20 minutes, and I need to do a little bit of prep for it. Just getting the things set up. But I will stick around for a few minutes and answer any questions anyone has. I'll also do any last people. If anyone still needs an ad code that's here, we can do that as well. Okay, so I'm going to go ahead and stop the stream. And thanks for showing up today. Thanks, everyone. Remember that the next class that we have is Monday. I know things have been kind of weird. But our next class will be Monday morning. It's a normal 2-hour lecture. And then next Wednesday will be our first lab. So Monday we're on Discord for lecture. And then Wednesday, lab. Okay? And that's going to be in person. So, all right. Yep. I hope you all have a good weekend as well. It's so weird that we had a class a week ago and then a weekend and now we have a class and another weekend. But that's how it goes. So, all right. Did I stop the recording? I don't know.